this computer. There we go. Alan, have you got any specific questions, or what would you say is difficulties, or as you say, you've done it last time, and is there anything that you wondered about?
I was going to talk about the quiz first of all.
Well, you probably did find errors in the quiz. I did take those out in the scoring. Yeah.
Yeah. How you said listed like 4 or 5 questions that had the errors of them.
Yeah.
There was like more than that.
Okay.
So, what was that? Sorry.
Can you give me a list?
I did take screenshots of some.
Very helpful. But not now. If you could email it, I'll look at it. But overall, if I can just say, each quiz in the end only count 1%.
Okay, yeah.
Basically, you know, if there are 2 or 3 points, it's 3.3% that's at risk. But so it's more for students to get an opportunity to say, yes, I know the terminology, because that's all the quiz is about, this terminology, mostly.
I still passed it anyway, even with the errors. So
yeah. So, but what I do is I go in and just make them count 0 towards the exam, and then it recalculates it. So
yeah. Okay. Yep.
So if you send me the list, I'll go and change them to 0. I can't remove them anymore because some students have done them. So
yeah,
then it blocks me. I can't change the quiz now.
Yeah. Yeah, no, it's all good. Okay. But there was more questions that that were kind of messed up than you'd actually put. So.
Okay. Well, tonight is all about probability, but just before we do that, I want to go back or just clarify, in the whole of chapter 1 is important. So if you want to make notes of that, the whole of chapter 2 is important, and the whole of chapter 3 is important. Chapter 4, you do not, well, you clearly can read it, but I'm not going to test 4.4. So 4.1 is important, 4.2 is important, and 4.3 is important. And 4.4 is not that important. Then numerical and descriptive measures. The main thing you should focus on is measures of central location, measures of variability. 5.3 is interesting because it's got box plots, but it's not that important. You can put it that way.
Box plots are kind of not that important, are you saying?
5.3, and 5.4, approximating descriptive measures for group data. Don't worry about that. Measures of the
So don't worry about.
Okay, let me make it clear. Worry about 5.1, 5.2, and 5.6.
Sorry, you're cutting out a little bit.
Okay. In chapter 5, you only have to look at 5.1, 5.2, and 5.6.
Okay.
Overall, read through the whole matter because it's a big thing, but if you want to focus on something, that's the stuff you have to focus on.
Okay. Yeah, okay, that's helpful.
And in chapter 6, you'll see I've got a slightly different approach. So for argument's sake, I haven't got a big emphasis on probability trees and so on, but let me quickly go through it and then I'll show you.
You haven't got a big emphasis on probability trees, did you say?
Yes, but I'll point it out again.
Yeah, that's actually where I'm struggling. Probability trees are probably like one things that I don't get. I'm bad with like I'm a very word sort of person, so when there's charts and stuff, I struggle to learn visually, so that's probably why.
We're then on opposite sides of the spectrum. I'm not a wordy person, so at any rate, I'm going to share the screen. Okay, and I'm actually going to start off with this particular example about breast cancer. Now, typically, all women go for mammogram, and then they have a positive mammogram, and then they go to the doctor, and doctors quite often make the mistake, and they say, you know what, the chance that you actually got the breast cancer is actually quite high. And this diagram actually just shows that if there's 1,000 women and there's 10 that's got breast cancer, 9 out of that 10 will actually test positive, but 1 out of that 10 will test negative and have breast cancer. Or on the other side, 1,000 people, if you start from the bottom end here, 99 women will test positive for breast cancer and actually not have it. Can you see that?
Yeah, yeah.
In fact, if a woman have a mammogram and it says it's positive, she still only have 9 out of 99 chance of having breast cancer. Don't know if it makes sense, but anyway, it's hopefully we'll get to it a little bit later again, and then you'll understand. What I'm really trying to say is probability, and particularly joint probability, is not simple. One actually have to draw this type of diagram to get to it. So let me just work through this. First of all, how in all of our lives, there's things that happen randomly. There's no way of predicting it. In terms of toys and games, there's definitely a dice. You can throw a dice and you don't know what the outcome is going to be. You can flick a coin and you don't know what the outcome is going to be. But simultaneously, you don't know what the temperature is going to be tomorrow. And you don't know whether there's going to be a tsunami somewhere in the world tomorrow. All those things can be associated with a probability. So if you know something is going to happen, but you're not sure what how likely it is, then we say that's a probability. Now, we need a way to describe it. And the first way is to just provide all possible outcomes. So if I look again at the dice, all possible outcomes would be 1, 2, and 3. Would you agree with that? 1, 2, 3, 4, 5, and 6. If I look at a coin, all possible outcomes would be head or tails. But let's look at more of a real life experiment. There can be lots of we can draw a sample of people, and some of them will be male and some will be female. Or on the other side, if we say we're going to draw one person, well, what's the probability of this person being a male, or what's the probability of it being a female? So for each and every occurrence that can happen, we assign a probability. If you think of how do we assign a probability? There's basically 3 possible approaches. One of them is make everything equally likely. In terms of the coin, it's 50-50. So we assign 0.5% to each possible event. On the other hand, if in real life we say, for instance, want to predict the weather, what's the probability of it's going to rain tomorrow, given a certain set of circumstances? What we can do is predict the weather and then actually check how good were our prediction. And then over a long time, we will be able to look at a frequency. How often did it actually happen? And then we can say, okay, going forward, that's the probability we're going to assign. So if you have a funny shaped, for instance, here's a little thing, I can throw it and measure, physically measure. I'm going to throw it 1,000 times and physically measure how many times did it actually land this way. And that I assign that probability based on the frequency of how things happen. You understand that?
Yes.
So you basically just keep on experimenting. And then there's the subjective approach, where you can look out of the window and just say, I think it's not going to rain tomorrow. And it's just your subjective view. Or you can say, I've got grown-up kids, and maybe when they were young, I could have said, I think one of them is going to be an architect. There's no real reason, I just think so. So I say the probability that he or she's going to be an architect is high. That's in our scientific terminology. And that's a subjective approach. Okay. Then there's a bit of classical approach, something I've just spoken to. Roll a dice, what's all the possible outcomes? Is 1, 2, 3, 4, or 5, or 6. I've got an experiment here that I often use in demonstrations. I should have pulled it out beforehand, but I didn't. It's a box that's full of red and white beads. And I've got I'm going to switch off the screen share so it just looks a bit better. Yeah. So if you look there, it's all the beads. And I can, with this, actually draw a sample of 50 beads.
Huh.
Now, in reality, I don't know how many red beads and how many white beads is in here. But you can count the beads. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14 beads out of 50. Is that right? No, 14 beads out of 50. But you can understand, if I do it again, so that time I got 14, now I got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 beads. So sometimes I get 9, sometimes I get 14, but I can do it 1,000 times and then work out the average. And then I can say the probability of getting, I can then work out the probability of getting 10 beats, the probability of getting 8 beats or 9 beats or 12 or 10 and so on. Can you see? I've just worked it out. Because I've done 1,000 experiments, I can now calculate.
And that's the relative frequency approach, right?
Yeah, that's the relative frequency approach. You're right. So we're already there. Okay, and here's an example of desktop sold in number of days. So 2 desktops were sold 10 days out of 30 days. I sold 2 desktops. So if I open the shop in the morning and I want to predict how many desktops am I going to sell, I know there's a high probability that I'm going to sell 3, because most of the days I'm selling 3 in any given month. And here is, if I take that same example, I've sold 0. One day I've sold 0. So the probability of doing that is 1 out of 30, 1 out of 30 days. 2 days I sold 1, 2 out of 30, and so on and so on. The probability always has to add up to 1. So you have to get one of those bits. Okay, and that's it. Okay. Subjective approach, I was talking about the weather forecast. Interpreting probability, no matter which method you use, all will be interpreted in the relative frequency approach. So we always interpret it. If I do this 100 times, 95% of the time I will get this, or 10% of the time I will get that result. So we always interpret it like it's a relative frequency. Okay. Here's two rules for assigning probability. One is all probabilities must be between 0 and 1. So 0.3 or 0.5. It can be 1, equal to 1. So if you're very sure something is going to happen, or you're 100% certain it's going to happen, you assign a 1. And but
well, then it's not a probability, right? It's like a certainty if it's a 1, right?
Yeah, sure. If you're very sure, yeah. At any rate, if you have different probabilities, you have to add up to 1. So if you have one thing and you're very sure and it's 1, it still adds up to 1. Okay. Now, here's, you can also have combinations of probabilities. You can, for instance, and we're going to look at some examples of that. In fact, I'm going to go to one of those examples right now. Say, for instance, here's a table, and it's about 10% of people are left-handed, and if 2 people are selected randomly, what is the probability of the following event? So you can see there, if the first person is, say, this top one, or the side one, I choose one person, and then I choose another person. You can see the probability that both is left-handed is 0.01. Okay? And that happens to be 0.1, 10%, times 0.1. And that gives you 0.01. Happy with that? If I just select one person and I don't care what the other person is, the probability of that one person being left-handed is 0.1%. And that is in line with what we have there. Similar, if I don't care who this person is, but I'm just caring about that, it's also 0.1%. Okay, so what is the probability of I selecting 2 people and they're both right-handed? Can you see that?
Were you meant to be still sharing the screen?
Oh, you should have told me, man.
Oh, that's all right.
Okay. Okay. Now,
that makes
sense. Okay. So what I was talking about is if the first person is left-handed and the second person is left-handed, the probability of that is 0.01.
Yep.
My question is, what is the probability that both people are right-handed? This person is right-handed and this person is right-handed.
Yep. So 0.9?
No, that is if one of the people, if you just care about one, you get 0.9. But if both must be right-handed? Okay, the bottom line, it's this one here.
Yeah.
0.81. Because the probability of this one right-handed is 0.9. Probability that this one is right-handed is 0.9. The combination of them, if you look carefully, it's 0.9 times 0.9. So that already gives you a tip. If you're talking of joint probabilities, you multiply the 2 individual probabilities for those events.
Yeah, right. That makes sense.
Sort of makes sense after you know it. By the way, this refers to your book to XM6 37, which is an actual example. Okay, here's another one, or here's a typical quiz type of thing. The quiz contains a multi-choice question with 5 possible answers, one of which of which only one is correct. The student plans to guess the answer because he knows absolutely nothing about the subject. What would be the sample space if he's got 5 answers? So he's got A, B, C, D. What A, B, C, D, E? What is the sample space? What is all possible things that he can choose?
Well, is this sample space just like 5?
Yeah. He can choose a A, or he can choose a B, or he can choose a C, or he can choose a D, or he can choose a E. Can you see that? That is the sample space. All possible outcomes is A, B, C, D, E. Let's ignore for a moment that he doesn't choose nothing.
Yeah.
Okay. What would you say is the probability that one of these is obviously the correct answer, isn't it? Because it's a quiz. What's the probability that he choose the right answer? He knows nothing. He's completely going to guess.
20% probability because it's 1 out of 5.
Yeah, that's correct. So it's 0.2. The probability for each outcome, A, B, C, D, E, is 0.2. So which approach did we follow here? Assigning that? The classical approach.
Yeah.
Okay. Okay. Can you give me an interpretation? What does this mean?
What does it mean? Well, it means if he's guessing the answer and he randomly chooses one of these options, he has 20% chance of getting it right.
Yeah, and what is his expected score? If he's got 100 questions and he randomly chooses them, what is the expected score that he's going to get?
Well, he's probably not going to pass, right? There's 100 questions.
Yeah, and each one has got a probability of 0.2.
Does that mean
okay,
is it the same?
Just think intuitively. The bottom line is he's got a high chance of getting 20%.
Yeah.
If you just randomly choose, you're more or less almost assured for 20%. Because
he's probably not going to pass, right?
No, 20% not pass. So you still need another 30 that he guessed correctly. Okay. At any rate, that's okay. So the next one is, here's raw data. And one of the things that you've done up to now is to do a pivot table. Remember that? In the previous chapter, to do pivot tables. Okay. At any rate, if you haven't, I'm going to show you now. So here we surveyed a lot of people. Some of them happens to be female and some of them happens to be male. And we asked them, what type of way do you navigate if you're in a car? You ask for direction, or you consult the map, or you don't ask and drive further. Okay. So one of the questions we want to ask is there a difference between male and female? So I'm going to do a pivot table. Click anywhere in the data. Click on Insert. Click on Pivot Table. Okay, I've chosen a new place. And I put gender over here. And I put in fact, I'm going to swap it around. I'm putting action over there, and I put gender over there. And I'm putting one of those variables there, and it counts it for me. And you see now in this frequency that we analyzed, you can see females 6 times out of 17 they would ask for directions, 8 times they would consult a map, and 3 times they would don't ask but just drive further. On the other hand, men, according to this survey, 12 times they just don't ask and they just drive on. Only 8 times do they ask, consult a map, and so on. Now, if
females are better drivers.
Okay.
Females are better drivers. No.
Is that your conclusion? It's not one of the measurements. But
they ask for directions more.
If I right click here, I can actually, okay, or in fact, if I do, I'm just going to make a copy of this, and I'm going to lose the fact that it's a pivot table by just copying it like that. Okay? And I'm going to change these words here, gender, and I'm going to action, and I'm going to change this count. Now, if you remember here in the table that we started off, we want to convert this so that it adds up to a 1 over there. Can you see that? So I'm trying to create this type of table, but from raw data. So here's where we are. So how do I do that? I do another thing, and that is I cut and paste this once more. And now I change this to say equal this divide by 40. And I make this I8 absolute. If you come across that in a course, and you can press F4, and then it inserts $signs, which make it absolute. Now it means if I drag this way and down, you can now see it adds up to 1. It adds up to 1. And now I can ask you, regardless of the gender, what is the probability that someone don't ask and drive further, regardless of the gender? Can you answer that?
0.375.
That one there, that's right. And I can now ask you all kinds of questions. I can say, if someone is a male, what is the probability that he's going to ask for direction? And it's clearly that answer there. Okay. Similar, if somebody is a female, what is the probability that she won't ask for direction? It's 0.075. And you can see there, it just so happens that these two, the probability is low that a woman will just drive on, and the probability is low that a man will just ask for directions. And this is how you interpret this. Now, this is actually what's called joint probability. And this, for me, is a pragmatic way to do it. And we'll look at that a little bit later. The complement of an event is so if the event is one thing, the complement of an event is everything except that event. Okay? But let's just go back. First of all, here's so we want to define the complement of an event, the intersection of an event. What's the probability of 2 events happen simultaneously? And we want to look at union of events. What if this event and this one happens? How do we calculate it? How do we work with exclusive events? What can we say about that? And then there's some concept called dependent and independent events. And then there's conditional events. So that's all the ways that we can calculate using probability. Now, there's always some mathematical symbolism. So how I remember this one, it looks like an upside down U. So that's a union. And what does it mean? It means that A occur or B occur, or both occur. So if I can take a simple example, if I throw a dice and I flick a coin, what's the probability that I get a 6 and a head? Can you understand that?
Do you just add them, times them together? So
we'll look at how we calculate that just now. So intersection is A and B. That's the one I just asked you about now. That's when both occur together. What's the probability? You actually multiply the two. Okay. This is called the complement, and it's written like this, and it says the probability A does not occur. So if we look at a dice and we say, what is the complement of the dice fall on a 6? It's if it falls on a 5 or a 4 or a 3 or a 2 or a 1. Okay. And here's what is the probability that A occurred given that B has occurred. And if you can remember that table we just looked at, I've asked the question there, what is the probability if you're a male that you're going to ask for directions? If the person we're looking at is a male and ask for it, that is, in fact, the last one we looked at, and I can't remember, the conditional probability. Given something, how does it change the probabilities? Okay. So my take-home message is create these little tables and use that to answer questions related to conditional probability. Okay. Here's the complement of an event. It's everything that's not the event. They go in the book through this as well. You know Venn diagrams. At any rate, this is the intersection. And the intersection, here's the symbol for an intersection. So the intersection is this area where both things cross over. Does that make sense? It's that middle. Yep. And the union of two events symbolically or in a Venn diagram is when A or B or both occur. Yeah. Okay. And there's some examples, but in my view, just remember this picture here. And this one here explains it all. So if I want to say, what shall I say? The complement of ask for directions, regardless of the gender, is 1 minus 0.225, isn't it? Or adding these two together. So it's not that one, it's both of the other ones. Do you understand?
So the complement's everything that's not in it.
That's right, yeah. So if I say, what is the probability that someone will not ask for directions? All I have to do is add those two together.
Yeah.
Okay. And similar, what is the probability that someone is a male? I extract someone in this data set, it's this number here, 0.575. Or alternatively, what is it that is not a male? It's clearly 1 minus that or this one.
Yeah.
Okay. So if you bear this picture in mind, you will generally be good and okay.
Yeah, I see.
And hence me saying, be aware of the tree diagrams and so on, but that is actually a cool way of doing it. Okay. Okay, they've got a couple of examples. I'm not going through it now, but here, if this is a dice, so all possible outcomes is a 1 or a 2 or a 3 or a 6 or a 5. The probability of a 1 or a 2, which is that one there, is the probability of 1 plus the probability of 2, which is a 6 plus a 6 is 0.33. Can you understand that? Sort of intuitively makes sense, doesn't it? Okay.
So is that's not any of those things like a complement or an intersection? That's just find the probability of A.
No, it's actually a union.
A union, right? Okay.
Yeah.
I still have to get all those names, remember all the names properly.
Yeah. It's actually okay. It's just a union and an intersection is the two main ones you need to remember. Complement is everything that's not that thing. So that's the only two that you really have to remember, and everything else gets described in those terminology. Okay. Okay. I want to get to an intersection. An intersection is if an event A and B occurs, and that's called a joint probability. Okay, I want to actually go back to the example which we started off with in conclusion. Just get it back there. Okay. You remember? Yeah, there. That's great. You remember we started off with 1,000 women, and how can we interpret it? And you can. I'm going to. I'm going to draw the equivalent block diagram of this here.
Okay.
So we know there's a test and it's positive or negative. And then you have a person have cancer, do not have cancer. Right?
Yep.
We know that if we add a little column here, total, and we add a little thing there, total, and we know that the total of all totals in our example is 1,000 people. Okay. So first of all, we know that on this level, 10 have breast cancer and 990 have not got breast cancer. Okay? So
yes.
We know 10 has got breast cancer and 990 does not have breast cancer. And you can see it adds up to 1,000, right? Okay, now we know that of those that have breast cancer, which is the people here, one has got breast cancer but tested negatively and 9 is tested positively. Can you see how I got to those two numbers?
Yep.
And similar, I'm going to get to this number, 891 will test negative and 99 will actually test positive, although they don't have breast cancer. Okay, now all I have to do is sum these two, because we know they have to add up like this, and similar, I want to sum these two, and I can, for a check that they add up to 1,000, which they should. Okay. Now I can do the same trick as I did before. I'm going to Control C and paste it here. And I'm going to divide this one by this, divide by that. And you remember how to make it absolute, F4, with those dollar signs in. And but I can drag it all the way there. Okay, so now I can figure out all these probabilities. So if somebody come in and test positive, the probability of that person actually have breast cancer is 0.009. Even though, so the bottom line is it's actually a very small probability. But people and doctors misinterpret that, and they think they misinterpret this picture, and they think when you walk in, if somebody walks in with a positive breast cancer test, they would say to them, 1 out of 9, you've got breast cancer. But it's actually a much smaller. The probability is actually 0.009. So it's 1%. It's still 1 out of 100, roughly speaking, that someone will actually have breast cancer. Okay. Anyway, again, this is for me a good way to explain it. Bear the table in mind, and maybe in this particular course is more focused on practical way of interpreting this than the maths. Now I can. So if you look in the book, there's actually all mathematical rules to do it. So there's. Let me just have a quick look here. I'm primarily interested in that you can practically interpret these type of diagrams more than whether you can do the maths.
Yep.
Any of the students, for that matter. I mean, they eventually get into this type of symbolism. Now I can do exactly this. I'll show you. Say, for instance, in this particular case, A is the test, and B is whether someone has got cancer or not. Well, let's look at this one here on top. I'm now sick of all these sickness things. But okay, let's look at male and female and how they ask for direction or not. So in this particular case, whenever you talk of a union, you look at all the things that's related to the union. So let me think of this. Say, for instance, the probability of A ask for directions and gender equals male. Okay, so how are we going to interpret this? It's a probability of being a probability of asking for directions, and we know that's 0.225, isn't it? Okay. Okay, I'm going to plus the probability of being a male. The probability of being a male is 0.575. Okay. Minus the intersection of A and B, which is this 0.075. Okay. So the probability that someone asks for directions and is a male is that one. An alternative would have been to say it's this one, this number here, plus this number here, plus this number here, plus this number here. Let's see if that works. Equal, I'm first just going to write it down, equal this number here, 0.15, plus this number here, which is 0.075, plus this number here, 0.2 plus 0.3. So the bottom line is, I'm going to code it. Where is my, and okay. Now if you look at the top one, it's this number plus this number minus that number. You see that's that formula? Now if I actually, I'm going to cut and paste it and actually do the calculation by removing this and put it equal to 4.725. Now let's see if this is going to work. I'm going to remove this. Oh, what happened? 0.725. Can you see? So this mathematical formula is nothing what you and me couldn't have done out of this table. So if you really, really just focus on understanding this table, you can do all of these things just by doing that.
Yeah, wow, that makes it a lot simpler.
Yeah. And similar, you know, as I said, yeah. So all of this type of formula, you can interpret it, just work through a couple of examples and you'll see you can always bring it back to a table like this.
Yeah.
Okay, probability trees is useful when you have more than one, but even this one I can interpret, I can just put up a table and that would be the same. So anyway, see how you're doing with it, and then we can look at it next week again.
Awesome.
All the best. Enjoy the course.
Oh, that's it?
Yeah.
Great. Thanks for explaining all that. That was really helpful.
Well, I also understand it a bit better now.
Yeah, cool.
Okay, I will post the recording, so if you want to look at anything else again, feel free to do so.
Great. Thank you.
All the best. Bye.
See ya. Bye.